Okay, welcome to the first note set in our third unit of our digital audio signal processing class. The third unit, I use the abbreviation FX. That is an abbreviation for effects. And if you have done or seen any sound engineering, you'll see that the sound engineers will often abbreviate the word effects with the two-letter FX. So that's why I'm calling this unit FX. This is our first note set of several, and we're going to be talking about effects based upon delay. We'll look at some other types of effects in subsequent note sets in this unit. There's some readings that I've listed down below. The two main ones are things that I've used primarily to base this note set on. The third one, I've used some of the graphics and I've used some of the concepts in that, but it's much more detailed. John DeToro has a three-part series on effect design. And if this is something you're really interested in, you really should track down these three papers and really consume them. So they're in the Journal of Audio Engineering Society. That's kind of the main place where you'll find journal articles on audio engineering. That and also the Acoustical Society of America has some as well, but the JAES is really the primary place. Okay. There's a whole family of effects based upon delay, and the idea is that we're going to use something called a delay line, and based upon or depending upon how we use that delay line, we can get any number of different effects. And in fact, many rack mount units or bigger pedal units might have all of these, because really we'll see at the end all of these are implemented with one common structure, and then you can just select some parameters to make it either one or the other. So we go from some of the basic echo type things, and the difference between slapback echo and regular echo is that slapback is characteristic of some recordings back in the 1950s. So people like Johnny Cash and Elvis Presley's early recordings had characteristic slapback. It's a very, very short single delay. You can hardly even hear it as a distinct sound. It just fattens up the sound of guitar and bass and things like that. And then echo is along those lines, although the delay is longer and you might have, and you typically do have, multiple decaying echoes. So think like the sound of the guitar on U2 recordings, things like that. Then we get into vibrato and flanging. Those are two things that are based upon delay effects, delay-based effects. So vibrato gives a shift in the pitch of the signal, just a little bit, makes it kind of wobble around. It's based upon or tries to mimic the idea of what a singer does when they hold a pitch. They just wiggle it around just a little bit in pitch. Flanging is something that you've probably heard. It's like that swooshing sound. Sounds like a swooshing jet taking off. And in fact, the reason it sounds like that is that the physics that's going on is exactly what's going on when a jet is taking off from the ground. And you may have heard that in, say, for example, 1970s recording by the band Heart. Barracuda, the beginning of that, clearly has flanging. Doubling is trying to simulate the idea of going back and recording a second take of something. So either guitar or voice. John Lennon was famous for, he didn't really like how his voice sounded, so he went back and would, in the early days, would double it. He'd try to sing it as close as possible. And then he got tired of doing that, and he said to the engineers, figure out a way that I can just sing this once and it'll sound like I sang it twice. The idea is to just make it a little fuller. You can't really hear, unless you listen very carefully, that there are two voices there. So it's not like you're singing harmony or anything. And then chorus is along the lines of doubling, except now we're maybe delaying it a little bit more and giving it a slight pitch shift that might vary ever so slowly. So doubling, you're not really supposed to hear that there is a second voice. It just makes the voice sound a little bit more robust. Chorus is really trying to make it sound like two people are singing in unison, slightly out of pitch, not in a way that's offensive, but just slightly out of pitch. And you can do more. We can do multiple voice choruses and things like that. So these two just use a fixed delay. The user sets it, so the user can adjust it, but once you're playing through it, it stays fixed. The other three uses a delay that is variably changed while you're using it. So we'll talk about how that all works. And it all starts with something called the delay line. So if we wanted a n sample delay, we would write the box z to the minus n. But what we want to do is have access to the intermediate results within that n sample delay. So we expand it out into a sequence of n unit delays. And this is really nothing more than just a set of memory locations. We can store a sample there, store a sample there, store a sample there, all the way out to store a sample here. So this would have been the earliest sample that came in, all the way up to the most recent sample that came in. So when you see these Z inverses, think of like a sequence of memory locations. And in fact, we will do just that. So this is a picture from John DeToro's paper that I just referenced on slide 1 of this note set. And so we need to think about something here. We need to think about the lines versus the cells. So we think about the lines lining up at the time instant of the sample. But then we think about the cell as holding the value. So sometimes we'll point to a cell and sometimes we'll point to an edge of this. And so it's important to graphically keep that straight. So here's the idea. We have this sequence of memory locations, and at every sample time n, so let's say n represents now, we have previously stored a bunch of samples in here. And so what we're going to do is move everything to the right. And this last sample here is going to fall off and be discarded. So everything moves to the right, and that opens up the first location where the most recent sample will come in. So if we label these in order of the actual time, so suppose n is maybe 100, after we store that sample at x of 100, so at this first position we'll have x of 100. Then in the next position over we'll have x of 99, all the way down to whatever we have. It depends on what we have here. By the way, this starts filled with all zeros. So when we get the very first sample coming in, it's just all zeros, and we'd have some non-zero values stored here, and then a bunch of zeros. And eventually things work their way in, and you're completely filled. So that's how this delay line works. Now, just a little aside, it's not particularly important on our focus, because our focus is just understanding the algorithms and not really getting into the nitty-gritty of how we implement these things. But if you are going to go and try to implement these things, you would want to use a circular buffer. Because up here, when we described this conceptually, we talked about moving samples to the right. Well, we don't want to have to go into our memory and physically move things. that would require a lot of extra computer processing. So what we're going to do is leave everything in place. We're just going to change our pointer as to where our beginning is, where our first entry is. So we can kind of think about this wrapping around. And we call this a circular buffer, but in an actual processor, it would be laid out in linear memory. But we would think about this last memory element being conceptually adjacent to that one. So we think about it as a circle. And then we just have a pointer that says, where is our 0 location? And we also have to have a direction. So that's this position. And as we move in this direction, we're going this way. So that means this one here would be our last element. And so here's how things work. What's going to happen is we're going to, we need to effectively move everything to the right and discard this oldest sample. All that means then is that we move our pointer to here. So remember, this was the this location, and this was that location. So if we move our pointer to there, that effectively discards the old sample. And so now our pointer is no longer there. And this is now the new, the current oldest sample. So that was here. So we've effectively moved everything to the right by just moving our pointer. So then our new one that comes in, our newest sample, gets written here, and it writes over the oldest one. And so now everything works properly. So now things are still going in this direction, and that's how things would work in an actual implementation. But again, physically in your computer, it's not a circle, but it's logically a circle. So you'd have to use some like mod arithmetic for computing your addressing indexes for that. But just wanted to point that out in passing. Okay, let's talk about single echo and slapback echo. So like I said, this was common in the early 1950s, particularly in recordings done in Sun recording studios in Memphis, Tennessee. So people like Carl Perkins and Johnny Cash and early Elvis recordings and things like that. So it's just the original signal with a delayed version, and if it's slapback, this delay here is going to be very, very short. And again, it's something that the user can adjust, but then set and leave while they play through that particular song. And when we look at this, we go, that's just that simple FIR comb filter, the very first FIR comb filter that we looked at. And we know what that looks like. We analyzed that before. We said, here's its block diagram. And we said, that's what its frequency response looked like. But here's the interesting thing. When the delay is long enough, the ear hears it as a delay in time rather than peaks and nulls in frequencies. So for long enough delay, we literally hear this as, we don't hear the ups and downs in the frequency response. We just hear it as a delay. So if you want the ear to not hear a delay, but to hear the nulls and peaks, then you need a short delay. So slapback echo is right on the verge of that distinction. And here's some ranges, some typical ranges. So for that delay, so here capital N is in samples. And here we're talking about our delay values in milliseconds. So you can convert those based upon our sampling rate. So you can get an idea of what the what the n value needs to be, typical values, and that will give you an idea of how big your delay line needs to be for these different things. Now you see that there is a gap. So if we're up to 20 milliseconds, your ear is going to hear it as peaks and nulls. But from 40 up to 120, we're just doing a slapback echo. And typically for slapback, the G value is set very close to 1. And then once we get beyond that, then we really hear it as a distinct separate echo. Slapback is just kind of like a sound right after the real sound. But a single echo, you hear the actual echo. Hello, 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 just like walking up to the Grand Canyon or a cave or something like that. So that's the distinction. By setting different delay values there, we can get 3 different effects here. And these are the 2 that we're talking about now. Okay, now we can get a multiple echo. So we just talked about slapback echo and a single echo. We can get a multiple echo. We don't want just a finite number. We'd like it to sound like the echo just keeps going, but it decays away. And so now we're going to use a feedback structure. Still will be a comb type filter that we've seen before. So we're going to have a delay of n samples. Again, that n is adjustable by the user. So really we would just lay out a range of memory locations, and then based upon the setting of the delay, we would adjust which value we tap out of. I guess I can go back and show you. We'd lay out the delay like this, and we might take our output from there for the maximum delay, or we might take our output from there for a shorter delay, or we might take our output from there for an even shorter delay, or maybe here would be the minimum value for the shortest possible slapback. So based upon where we draw out our last value. The rest of it can work just as normal as as it would for any delay, but we're just taking our output from different locations. So, so we have this delay set to some amount of delay, and we're taking the output and feeding it forward, the output of the delay, and feeding it forward into the ultimate output. But we're also feeding it back so it goes through the delay again. So this is the hello, 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 hello. And depending on the amount of delay that you have there will determine the time spacing between those repeated hellos. And this value here, I didn't really make them get softer as they went, but that's what effect that would have. So if we analyze this, I didn't go through the steps, but you should be able to analyze this and come up with the transfer function for that. But we can also get there by just thinking about, I've drawn in this intermediate result, y1 of n, and that's easy to figure out what that is. It's x of n minus 1, and so that's this thing coming through, and then we get this fed back many, many times. So that's the idea of what this result is here. And then the actual output is that result times GF plus an x of n going straight through. And so now we just write x of n, we take all of this and put it in here, times G sub FF, and we have figured out what that thing will look like. And now we can see that it's this sets the feedback, and that's going to set this decay rate of the echoes. And you can see that also here. So if G sub FB is a number close to 1, that will decay slower than when G sub FB is a number much less than 1. And typically these are set to be positive numbers, so set between 0 and 1. And then this just controls the level of the whole echo thing relative to the original. So 2 nice controls. Okay, how can we make this better? That what we just showed sounds a little sterile, and in some applications that might be exactly what you want. But these things were originally done in analog electronics with something called a bucket brigade delay. I think I give you a pointer to where to go read about that in just a little bit. And the analog electronics used in these so-called bucket brigade chips caused a degradation each time you went to the next delay. Each time you went through the delay line, the signal would get degraded a little bit by a low pass effect. So the highs would get rolled off. And so we can mimic that in our digital systems by putting a low pass filter up here in the feedback. And then you can play around with, parameters for that. You could actually have a knob to control the cutoff frequency or something else about that, maybe the order of it, something like that. But that's the idea. So each time the echo goes around this, it goes through this low pass filter and keeps getting degraded. And so we can use that to model the old analog waves. So the earliest type of delay was just done with a tape recorder. So you would record something and then you would read it off and then re-record it back onto the tape. And you would control the amount of delay by adjusting the physical distance between the record head and the playback head or the read head. So that was the oldest way, and that continually rewriting onto the tape, reading and recording onto the tape caused a degradation that we're modeling with a low pass filter. And then things were done with analog bucket brigade delay chips. And if you want to read about those, go to this web page. That's a great web page. If you're interested in guitar effects, they go through and analyze lots of different classic effects, show how to build them and things like that. So if you're interested in this course, go there as well. But that's mostly analog stuff. So anyway, you can go read about how bucket brigade devices worked. And then we can also do multiple taps. So we could have multiple delays here that we're tapping off of, and something called a ping pong delay. I don't really want to go into the details of those, but if you look at reference 1 from slide number 1, track that down, you can read about it. And you can also Google about those things. All right, so delay, pretty easy in concept. Getting it to work and sound right might take some doing, but the concept is pretty simple. So let's move on to our next effect, which is vibrato. And just a little bit of history on some terminology here. The word vibrato corresponds to variations in pitch. So like I said, that's what a singer might do when they're holding a note, or a violinist wiggles their finger back and forth when they're holding a note, and that causes a slight variation in pitch. Or a guitar player like B.B. King, famous for this, they don't wiggle, you can wiggle your finger up and down the string like a violinist does, but a guitar player tends to stretch the string across the fretboard and literally change the tension in the string to create a change in pitch. So that's vibrato. And our job is to try to figure out how to mimic that in digital audio signal processing. So it won't be like what a musician does where they apply it only on the held notes. It would be applied all the time. So it is a odd sounding effect, but people have used it to great musical effect in the 60s and 70s and onward. So that's vibrato, variation in pitch. There is a another effect called tremolo, and that's just a variation in amplitude. And I don't even really talk about that in this note set or any of these note sets because it's so simple in concept to implement. The trick is just getting the right shape of the up and down in amplitude. But that's tremolo, variation in amplitude rather than pitch. Now, unfortunately, Fender got those backwards originally and still keeps using them backwards. So back in the early 1960s, they introduced amplifiers. Here's a picture of the Fender Deluxe Reverb, and it had a tremolo circuit in it, but they called it vibrato. So you would plug into the vibrato channel to get tremolo. So there's speed and intensity controls for the variation in amplitude. And then when they came out with the Stratocaster, well, actually that was before they came out with the vibrato. Although I may have misspoke. I'm showing it on a Deluxe Reverb. I think on some of the Tweed amplifiers back in the 50s, they also had tremolo. But anyway, right there is the vibrato arm on the Stratocaster. And basically by pushing up on this, or pulling up or pushing down on that, you can rock that bridge back and forth, and it either tightens or loosens the strings. Well, that's going to change pitch. But when they patented it, they called it a tremolo device. It does not do tremolo. You would do tremolo by taking your volume knob and rocking it back and forth. So this is clearly vibrato. So Fender has them backwards, so you need to be aware of that. So we're interested in vibrato, and we need to come up with a way that periodically shifts the pitch of a signal. But we have to be careful in how we shift the pitch to make sure that it stays musical, because there's a couple different ways we can think about changing frequency, and frequency is related to pitch. So we need the way that's going to sound musical. And that is based upon concepts of Doppler shift, because something will remain musical even if you're listening to it with yourself in motion and the source being fixed in position. So what we're going to do is imagine that there's a source out there that is periodically moving toward and then away from us. That's the effect that we're trying to capture here. That's vibrato. So since the distance is changing periodically, that means the time for it to go from source to listener is changing. So the delay between source and listener is changing periodically. And that's what creates the Doppler shift. So let's look at this from a continuous time point of view and just for a sinusoid, because we're interested in musical applications of this, and we can think about any note, isolate a note, and we can say, okay, that's essentially can be thought of as a sum of a bunch of harmonically related sinusoids. We're stretching the idea just a little bit here, but that's the basic idea. And so let's look at a continuous time sinusoid and impart a changing delay to it. And we'll denote that delay as d of t. So here's our sinusoid at the source, and then at the receiver, at the listener's position, it's going to be received looking like this. Now, if the distance between source and listener were fixed, then this wouldn't be time dependent. But now we're going to make that time dependent. We're going to imagine that the source is moving back and forth toward and away from us periodically with some appropriate rate and period. Okay. So let's look at the concept of instantaneous frequency. So instantaneous frequency, we talked about that before when we talked about swept sinusoids and so forth. And we saw that the instantaneous frequency was the derivative of the entire thing inside the sinusoid. So there's the thing inside the sinusoid. And we take the derivative of that. Well, the derivative of that term gives omega 0. And the derivative of omega 0 times d of t is omega 0 times the derivative of d of t. Okay, perhaps a bad choice of symbology there, but I think we can persevere through that. So we see that to periodically change the frequency, we need a changing delay that will also change periodically. And we see that the change in our frequency is related to the negative of the derivative of the delay. So we need to keep that in mind when we're doing this. And one further thing to note, because we're doing this frequency change based upon this time varying delay, the harmonic relationship between the notes will always remain the same. So here's our original harmonic relationship. So that's why we were considering a single sinusoid, but now let's think about a single musical note. It's going to have components, at least essentially, at a bunch of different harmonics, and this would continue down, however many non-negligible harmonics we would want to consider. So each of those, what do they get changed to? Well, here's the frequencies that they get changed to. Now note that the ratio of those is 2. That's why they're harmonics. And the ratio between these is 3. That's why that's that harmonic. Well, look, the ratio between these two, the omega 0s cancel, that cancels, still 2. And the ratio between these two, omega 0s cancel, that cancels, still 3. So that's why we use this way of changing frequencies, because it maintains that harmonic relationship, and that's what keeps the new sound being musical. Now, there is another way to change frequencies that you probably learned about in your signals and systems class, and you used in maybe a communication systems class, where you take a signal and you multiply it by a cosine. And we called that in signals and systems modulation or frequency shift or something like that. If we were to use modulation instead of this changing delay, then this would not work. We would not get harmonically related frequencies after we do that modulation. So modulation has its place, lots of places, but just not here. So if we look at, this is basically the same thing that we looked at before, but going the other way, right? Here we were looking at ratios this way. Now let's look at ratios this way. And so that ratio, this thing cancels out, and it's that quantity, 1 minus the derivative of the time-changing delay. So we need to think about how we're going to specify that d of t. We need to have something that's changing that. And in most musical applications of this, digital audio effect versions, not physically wiggling the string in one way or another, or wiggling your tremolo bar, as Fender calls it, or vibrato bar, as everyone else calls it. We need to have some sort of electronic way of creating that delay. So let's write an equation for the delay. There's going to be some midpoint, right? The source is moving back and forth. So there's going to be some midpoint, and that's the delay corresponding to that. And then we have a sinusoid that by itself is going to go between plus and minus 1 with some frequency. We don't want this to be a super high frequency, just a small frequency. Think about what a violinist does. Just slowly wiggles their hand back and forth, that kind of thing. And then we put a W out in front so that we can say okay, this is how far we go up and down around that. So compared to D mid, this value might be fairly small compared to that. But in reality, I mean, what we want to make sure is that when the sign hits a -1, we want the total delay to not be negative, because I'm not sure what that would mean. That would be an advance in time. So we just need to keep W to be no bigger than D mid, and then we'll be fine. So this FLFO, that's the low frequency oscillator's frequency. So this is the signal that the LFO creates. And we'll see that in our figure. And sometimes that's included as part of the LFO, but it's a parameter that we can adjust. So now using that, we're going to take the derivative of this thing. So the derivative of D mid goes away because that's a constant. And now the derivative of a sine is a cosine. And so we get something that looks like that. Well, and we also get the 2 pi FLFO that comes out in front. So that's just Calc 1 all over again. So now we see that the ratio between the old or the new frequency and the old frequency depends on two things. So we can watch this over time, and this will tell us kind of, if we look at the peaks, the largest and smallest values of that, that's going to tell us how this thing is going to change in frequency, how far up and how far down. Well, it's going to be symmetric, as we can see here, or at least from a ratio point of view. But the extent of that is going to depend on two factors. So there's kind of an interaction between the delay width and the LFO's frequency. So that's something that isn't obvious when you start off thinking about these things. So let's think about some typical values for these things. Remember, we want things to stay pretty musical. Although you can set these effects to give some pretty bizarre, crazy sounding things, but let's just get a feeling for what might be some ordinary parameters. So if you check out what people do on violins and guitars for vibrato, it's something on the order of about a 6 hertz rate. And the amount of ratio change is typically pretty small, just a plus or minus 1% change. And so if we analyze this using this as FLFO and using W, we can find out that to get this kind of 1% change up and down in that ratio would be just a fraction of a millisecond. That's the width. So not very far around that D mid. So remember, D mid, irrelevant. You just want to pick D mid big enough so that when you, whatever you set your maximum width to, you don't run out of delay cells in each direction. And just as a point of context, we're talking about an up or down by 1%. A half step change in pitch. So on a piano, that would be between any two adjacent keys, white or black, but find two white keys that are next to each other with no black key between them. That's a half step. And on a guitar, just one fret. So play an open string and then press it down on its very first fret. That's a half step. That's a 5.9% change. We're looking at only a 1% change. So it's very small compared to, the changing from one note to a next in the scale, in the chromatic scale, so to speak. So that just gives you some context. Now, can we design something that would be excessive in these parameters? Yes, and maybe we want to go beyond that just to allow the user to have some wild and wacky sounds available, but we also want to make sure that they can set it to something that is a little tamer. So what's the form for this vibrato? Well, we've already said what it is. There's no original signal being added back in, but it's just a delay line. But the difference here is that the delay line's length that we're tapping out of is going to change. So we show it here as a box with a delay, capital M, that's changing with N. So I'm mixing and matching things from different sources here. So that would be the equivalent of that D of T that we had before. So sorry, changed notation, but I'm just trying to stick with what's in the books to some extent. And so the amount of delay that this is actually imparting at some instant of time is being controlled by the LFO, or the low frequency oscillator. Now, we don't actually build it this way with a delay that, we think about, adding or subtracting, or, including or removing delay cells. Nope, we just lay out a big long delay line and then just change where we take our output from. So that's the idea. And so now we're saying here that, okay, we said 6 hertz was typical. We're going to maybe go up to 15 hertz as our maximum LFO frequency. Maybe you could go a little higher than that, but beyond that, it's going to sound really weird and wacky. If you're wondering how to make one of these digital LFOs, well, John Totaro has a paper on that. It's part 3 of his 3-part effects design series of papers, where he talks about oscillators, and that is in the Journal of the Audio Engineering Society. So you can track that down and read about it. I'm not going to talk anymore about that. It is important, but I find it to be the less interesting parts of this. Okay, let's talk about this time varying delay line. So here we've got laid out our delay line. I'm laying it out linearly. Remember, we would really do this circularly. And instead of thinking about this is where we take out, instead, we're just going to say we're going to move this back and forth around some nominal delay or tap center. And this would be what we referred to as D sub mid before, at least in time, in milliseconds. But here we're talking about a location. So some location in the middle, that would be our center nominal delay. So if the LFO is providing a 0 value, the output is being taken from that position. And then as the LFO swings positive and negative, it will move the position that we're drawing from right and left around this nominal delay. So that's basically how this thing works. So this is a nice MATLAB view of how we would implement this, but this is not how we would do this in an actual implementation. But the idea is that we've defined a delay line variable, and it has n elements in it, so we drop the last one off, and then we stick it inside the new delay line with a newest sample at the beginning. So that is how we do that. Now, one of the hard things is our math is 0 oriented, or 0 origin oriented, but MATLAB is 1 origin oriented. So when you're thinking math and writing MATLAB, you have to be clever enough to keep track of that. So now we've got this delay line, and that's just continually going. We're just continually shoving the new sample, every sample spacing, we're shoving a new sample into our delay line. In MATLAB, you can't really do that in real time, obviously, but you could just run a loop and just think about sticking this in and then save those and then play them back later. But in a real implementation, just every 1 over fs, you're sticking something into the delay line and dropping something off the end. But we're also moving where we read out. So that's going to be adjusted by the delay signal, which I'm denoting here as D of n. So we've switched to a discrete time version of that. So like I said, the current readout position is either left or right, depending on the LFO value of the nominal delay, which is D mid, the tap center. So how fast we go back and forth is set by the LFO speed. So there will be a knob or a control that the user can set. And there's also a width. So the width control sets how far we can go to the left and how far we can go to the right as the LFO sweeps through its positive and negative values. So we need to make sure that our W is no bigger than the number of cells to the left and the number of cells to the right. I typically, when I build these in MATLAB, I put a couple extra cells out there. There's no harm in doing that. I just need to make sure that I don't overrun my array. And the same thing in real-time implementations. I might put one or two extra cells out there, and we'll see that we really do need at least one extra cell on this side for doing something that we'll do that we'll see in just a minute called interpolation. And so let's lead into that idea of interpolation. It turns out that for these cells, they're separated by T sub s. That's just 1 over Fs. And for a typical sampling rate, that's a pretty coarse granularity of allowable delays. And it turns out it doesn't sound good. So, and we'll see why in just a little bit. So that means we're going to have to interpolate between these cells. So in other words, the W times the LFO signal, so the amount of delay, that's going to give us a value that might actually lie between two of these values. So remember I said to think about these vertical lines as the precise positions of the sample. So the sample that's held here occurred at that time, and the sample that's held here occurred at that delay. But our pointer might go in between them. And so what we want to do is get a more accurate reading of the delay value or the delayed signal value at that intermediate delay, but we don't have that value. So we have to interpolate the values. And so let's take a look at that. So again, here, remember these lines here represent the positions, the actual delay values of the samples that are stored here and here. So here is that line and here is that line. And so we're talking about delay. So if this is going to be delay of I, this one has a delay one more than that. So that's going to have a delay of I plus 1. So the sample stored here is actually x of n minus I, and the sample stored here is x of n minus I plus 1. So 1 point earlier in time, but to the right in the delay line. But the sample that we really want is somewhere in between those two. We don't have that sample. So we need to figure out what it is. And so what we're going to do is define the value of the delay, the location of this delay, with an integer part and a fractional part. So this is the delay value that we compute. Comes from taking nominal delay times the chorus width, that's what we called W before, times y of n, which is our LFO signal that goes between plus and minus 1. That's the sinusoid that we looked at before. And W is a positive integer number of cells, but this is going to be a number that, except at its extremes, is non-integer. This is an integer. So we're going to have an integer plus an integer times potentially a fraction. So our delay value will not be an integer, meaning it's not going to point at one of these two positions, I or I plus 1. So we write that as I dot frac. I is going to be the integer value, so that's nothing more than this value here. And frac tells us a number between 0 and 1, how far between these 2 points we would like to have the actual sample. We don't have that sample, so we can't go back and actually sample it. We have to fake it. We have to approximate it. And so what we're going to do is use the concepts of interpolation. So now that we've got these concepts defined, we have this number, we have this number, and we want to use those together with the value frac to figure out what sample value approximately should we use for our interpolated delayed signal. And so that's the idea. And that's all I'm saying down here mathematically. We'd like this value here. We'd like it to be equal to that, or it's not going to be exactly equal. And there's several different ways that we can do this interpolation. Well, linear interpolation is the easiest, and you should be familiar with how to do that from other engineering applications. You got two numbers, and you want to know, what lies, a quarter of the way between them. You just draw a line between them and use that. And then we'll see some other approaches based upon an all-pass filter, based upon things called quadratic or cubic splines. And then there's other approaches. And if you want to see those other approaches, you can go to the DAFX book. But I'm going to make an argument in subsequent slides here that you'll do okay with that. But you can do what you want. So let's take a look at linear interpolation. So again, here's our sample delayed by I. We have that value. And here's our sample delayed by I plus 1. We have that value. And again, I'm pointing out, I'm showing this on a delayed line, not the time axis. So this is the order in which they are in the delay line. Okay. And what we want is the value here that is frac away from the I delayed sample. And what I'm going to do is, to get an approximate to that value, I'm just going to draw a straight line between the two values that I have and go over frac and say what's on that line. And that's the value that I'm going to take. And I think you can convince yourself that that is the right equation for that. Let's just do a couple test points to see. So we've got frac and 1 minus frac. We've got our I plus 1, so that's this value. And we've got our I, that's this value here. So first, let's just look, what if frac is 0? That means we should get this value. Well, that goes away, and this becomes 1, and we're left with the right value. What if frac is 1? We should get this value. Well, frac is 1. That keeps this, and that goes away. And yes, indeed, we have that. What if frac is a half? Then we should get the point that's midway between these two. So if frac is a half, this becomes a half. 1 minus frac becomes a half. And that's just the average of those two values. And in fact, that is the value in between. So this looks like a line. So the line is a function of frac, and it is a line. And it matches up exactly what we want. So we've convinced ourselves that this is correct. Now let's think about this as an effective filter on the signal. Now, what we're going to do is say, well, this has I in it. So there's going to be a delay of I that we can just factor out. We don't have to worry about the effect of that. That's just a pure delay. So I've factored out, I've just rewritten this here as Z minus I times 1 minus frac. That's this. So the Z to the minus I comes from that. And then we have frac operating on this. And so frac times z to the minus I plus 1. So now we've interpreted the effect of this as a filter. So we were thinking about these as being in a delay line, but and that's how we physically do it. But to analyze its effect, we now flop it around and think about these as being samples coming in to a filter in the order that they would come. And so we have that. Now notice that there's a z to the minus I here, and there's a z to the minus I there. So we can factor both of those out in front. That handles the integer delay part. That's the easy part to analyze. We can just forget about that. That gives us the I sample delay, and then just analyze this part. So let's just look at that. And so now I've just extracted that part out, and I put a tilde on it so that we can keep track that it's a little bit different than this thing that has the I integer delay part. Okay, this is the thing that's going to impart some frequency response to the signal. So let's look at that. We can analyze that, find the frequency response, and look at it. Well, I just plotted it for a bunch of different frac values using freq-z, simple two-tap FIR filter. And it ended up looking like this. So here is that thing converted into magnitude of its frequency response. I've just plotted between 0 and pi. I'm showing a normalized frequency. So the units of capital omega here are radians per sample. And we see an interesting thing. When frac is equal to 0 or 1, we get a nice perfect flat frequency response. That's what we want. But let's look at the extreme. When frac is equal to a half, we get this very severe low-pass filter. But remember, that frac value is changing. It's constantly changing between 0 and 1. Technically between 1 and minus 1, but we can just analyze it between 0 and 1. And so as that LFO sweeps the delay, this filter is time varying. So we have a time varying filter because frac is changing with time. So technically we should write frac as a function of n. But all I'm doing here is saying, let's look at this for a bunch of different frac values. So I'm showing here 0.1, 0.2, 0.3, 0.4, but the intermediate ones are half that, okay? So what is that doing? It's imparting a time-varying low-pass filter. So the low-pass filter is going to create some muddiness on our signal, but it's going to fluctuate. So there's going to be an audible flutter here, which is not good. So I'm just pointing out here that you need to remember that this filter is changing over time, and that's what will lead to this audible flutter. So that's not good. And in fact, it does not sound good. So if you were to just use linear interpolation, you'd get a flanger, but it wouldn't sound, or you'd get a vibrato, but it wouldn't sound very good. It's getting ahead of myself, getting to flanger. Now, we should look at the phase delay to see if we're getting the actual fractional delay that we think we want. And that turns out to be pretty good, actually, at least at low frequencies. So below Fs over 4, remember this corresponds to Fs over 2, so below Fs over 4, these lines are pretty flat, and they do match up pretty much to the actual delays that we want. So the delay seems to be working at least at low frequencies. At high frequencies, not so good. Now, remember, if we're applying this to a guitar, guitars don't have much frequency content above 5,000 hertz. So Fs is 40-ish. We'll just stick with 40. So Fs over 2 is 20 kilohertz, 10 kilohertz, 5 kilohertz. So we might be okay. But still, going back here, we're still going to get some significant fluctuation in some audible flutter. And so this won't work well. So that's a problem. Now, one way that we can address this is to just increase the sampling rate before we apply the vibrato. So we upsample and filter to get rid of the images. So this is the increase the sample rate, and then put things into our delay line. So now what that means is, say we just went up by a factor of 2 in sampling rate. This is now 40. Whoops. Right? Our sampling rate might be on the order of 80 kilosamples per second. So fs over 2 is 40 kilohertz. This is 20. This is 10. This is 5. Really good. Let's look over here. Now we're down to here. We still get a little bit of fluctuation, but not that much. Okay, so we could go up even farther. We could go up by a factor of 4, and now we're going to be operating primarily down there. So that could work. But the problem is that's going to require a lot more delay cells, a lot more computation, and so that becomes costly. Might be fine for your application to do it that way, but might not be cost effective. Think about what we're doing when we upsample. We're really making the delay spacing in our delay line much finer, so it almost reduces the need for interpolation to some extent. So that's kind of what's happening there, but kind of a brute force way to fix it. So just summarizing some of the problems here. We've got this low pass filtering. Might not be a problem, but probably will be. Muffles the sounds, creates an audible flutter. This non-constant delay over the higher frequencies is going to disperse the sounds. The high frequencies will not go through and line up properly, so the sound will not be perhaps as good as we would want. So it's conceptually simple, but just doesn't work very well. And this muffling and flutter is the big thing. And we could fix it with increasing the sampling rate, but that's kind of a brute force way to do it. All pass. So the problem here is that the linear interpolation is fundamentally a low pass filter, but maybe we can come up with an all pass version of interpolation. And in fact, we can. Now, I don't go into all the details of where this filter comes from, but I just kind of put it out there. There are places in the literature where you can read about it. So here's our linear interpolation, just revisiting that. And it ends up with a transfer function that looks like that. And now all we're going to do is change this into this. This now becomes an IIR, all pass filter, and the transfer function looks like this. So notice that we have the kind of cross-related coefficients. So this is clearly all pass, so it will not create any kind of muffling or flutter, because regardless of the frac value, the magnitude will be perfectly flat. So we fix that. The question is, does this give us the right delays? So we really need to look at that. And so here I've plotted the phase delay in samples, and I'm doing frac 0.95 all the way down to frac equal to 0. And you can see at high frequencies, it is also very, very bad. But if we come down to more reasonable values, okay, down here, it's pretty flat, but there is a problem here. Notice that these things don't even really line up, right? Do I talk about that? Yeah. Let me just comment on it here. So this is a frac of 0.95, but the delay that we're getting is just a little bit above 0.9. And then this should be 0.9 here, and it ends up being just a little bit above 0.8. So things don't line up quite right. So even if we limit ourselves, using the idea that the sampling rate or that the guitar signal is only out to about 5 kilohertz, things aren't being delayed the amount that we think they should be. Is that a problem? So looks like we've made the delay performance worse. We've completely fixed the muffling and fluttering. We're not even getting the correct delays at low frequency, let alone the fact that they swoop upwards and are not constant overall frequency. Now, Detaro, if you go read his paper, he does go into a lot of detail about using some sort of warping approach to fix that, only to some degree. And when the dust settles, here's what he said. This is a direct quote right out of his paper, so you can go read that. And you can pause the video here and read it right here. But the TLDR version it sounds pretty good. And the reality is that, is a user really going to know when they're adjusting the vibrato values that the delays are not quite mapping up? They're going to just turn that knob until it sounds like what they want. And so if things sound okay in the music application, things are okay. We don't have to fuss over, in some things, we don't have to fuss over the precise mathematical specs of something. Does it sound good? Does it sound like vibrato? Can the user set it to the way that they want it to sound? With the all pass, it works quite well. So you can then go on to higher order polynomial interpolation. So in the DAFX reference that I gave, they do that. So we could fit a second order polynomial rather than a first order line. That would require 3 samples. And the thing that's weird about that is you'd have a sample, and a sample, and your fractional delay might be pointing there. So you're interpolating based upon 2 that surround the point that you want and 1 that's just way out there. So that's what you would have with a second order polynomial. Makes more sense to include another point out here. So now you're using these 2 to the left of the point you want and these 2 to the right of the point that you want. That makes a lot more sense, and that leads to cubic interpolation. So you would use 4 positions. So here's 1, 2, 3, 4 positions. And now this just comes from the theory of cubic interpolation, where we get these coefficients out in front. So if you want to read about that in a numerical analysis course, you can read about it there. Or you can just take it as given. And here's some MATLAB code that I've corrected. At least the edition of the DAFX book that I had an error in here, so it interpolates the wrong interval. That might have been fixed in more recent editions of the DAFX book, but I don't really know. But this is correct as it is stated here. I just corrected it and rewrote it in the notes. We can find the transfer function for the cubic interpolation. I'm going through this quick, and there's going to be a reason. We'll see that it's kind of overkill. Don't really need it. There's our transfer function for ignoring the delay by A that we can pull out in front. So we pull out a Z because there's a Z plus 1 there, so we can pull that out in front and just look at that. We can account for this Z by subtracting 1 from the delay of the term with the curly brackets around it. And here's a plot of that. So I'm just showing you some code that I used. I'm just using freq Z, and I'm looping through a bunch of frac values. And we see that, okay, it does fix the flutter, but it doesn't fix the low pass muffle. Gives us great performance on the phase. Does a really good job on that. And by the time we get down to here, the flutter is almost non-existent. But we still have that low pass kind of drop off. But we can always fix that with some sort of fixed high pass filter that we put after this to just boost these values back up. So that's possible. Requires a little extra design work and a little bit extra computational complexity. Much better performance on the phase delay than either linear interpolation or all pass. It's like perfect, straight on, right on the values that we want. But remember, Totoro said, the all pass, even though it doesn't match numerically and precisely the numbers, it sounds good. Musicians can use this quite readily and they like it. So why bother with the cubic? I'm not sure that Totoro said that. I'm not sure he even considered the cubic in his paper, but that's what I'm saying. If the all pass works well from a musical application point of view, there's really no reason to go to all the overkill to make this happen. And we still have to fix this with some sort of high pass filter. So, okay. So that's vibrato. Now let's move on to flanger, our third effect based upon delay. So this is an old trick that recording engineers and producers did back in the day, back in the 60s, and maybe even in the 50s, with reel-to-reel tape players. So I'm showing two reel-to-reels. So we have a reel of tape here that, and then it moves in this direction past a reed head. So as time goes on, the tape rolls up onto here. So that's how a reel-to-reel tape recorder works. And this reel here is just a plastic reel that the tape goes on. And the edge of it is called a flange. I mean, technically, maybe there's like a little disc here where it's held on, and that might technically be called the flange, but it doesn't matter. The idea, here's how it works. You start playing two identical tapes. So you record something, and then you make a copy of that, and you put them both on a tape recorder. So you got two tape recorders that are in playback mode. And somehow you align those just perfectly so they start off aligned. So you start them at the same time. And then as they're playing, so you can make these tape recorders so that they're synchronized in some way. But as they're playing, what you do is you just touch the flange of one. That's going to slow one down and create a time-varying delay. And then you release this one and you touch this one and slow that one down. And so what you're doing is creating this time-varying delay that's going plus and minus between these two, just like we talked about in the vibrato, except now we're adding the original. There's two things that are adding together, unlike the vibrato. So we already know how to implement this. We know how to do a time-varying delay. We know how to use the all-pass filter to do some good interpolation. So we can do that. But let's think about the physics of what's going on here. Think about an airplane, jet airplane, flying near the ground. So here's the ground. And you're listening over here. Yes, you have a really big ear, or that airplane is very far away, one or the other, but that's not really the scenario we're trying to think of. We're thinking of the airplane being close and close to the ground. So I'm showing two paths. In real world, there's more than two paths, but two dominant paths. One that goes directly from the airplane to your ear, and one that goes and bounces off the tarmac or the ground and goes to your ear. Now, obviously, the straight line is a shorter distance than the bounce. So this delay, D1 will be shorter than that delay. So we now have a time-varying relative delay between these two. And since this is moving, these will be changing. So that's the idea. And we know that delay causes constructive and destructive interference. You learned about that in your physics class. You take a sinusoid, you delay a version of that sinusoid, and when those two sinusoids end up being such that when one goes up, the other one goes down, they will cancel each other out if they're added together. That's destructive interference. But if when one goes up, the other one goes up, that's constructive interference. And so now think of sound being made up of many of these different frequency components. And so at some frequencies, you're going to have constructive interference happening, and at other frequencies, you'll have destructive interference. But as the relative delay changes, where those constructive and destructive interferences happen in frequency will change. So the time varying delay causes frequency changing or frequency shifting destructive and constructive interference positions on the frequency axis. And that creates a whooshing sound. And that is the characteristic sound of a flanger. So like I said at the beginning of this note set, take a listen to the intro to the 1970s song by the band Heart the song is called Barracuda. The intro to that is classic flanger. Let's look at it mathematically. So what we need is one signal added with some weight to a delayed version, and this delay is going to be time varying. So we know how to get this. We run the signal through a delay line, we sweep back and forth our output point, and we interpolate the cells to get that value. So I show it here as just a delay, but that's what we just talked about for the vibrato, and the LFO is changing that delay value. So this is just a conceptual view of it, not the physical view of it. So the signal goes through there, comes out with some delay that's changing, gets multiplied by G, and we add it to the summation. So that's exactly what we were doing here. Differential delay between the two and adding them together. Now we're not showing the G value, but we could put a little amplifier in each position and adjust the level of each of those two signals accordingly. So that's what we have. So very easy to model in the transfer function view. It's just a simple FIR filter, but with a time varying delay. So that's what makes it interesting here. But it's a comb filter. And in fact, it's that simplest FIR comb filter. And we studied that. We know about the locations of the nulls and peaks. So we can go back and look at our notes for the FIR comb filter, and we can deduce where the nulls and peaks are based upon that theory. So here's just a couple examples. I'm using just two sample delays. That's much smaller than what we would really have for a flanger, and we'll see what the typical delays are. But so for audio, a two sample delay is going to be something on the order of 45 microseconds, so not an awful lot. So keep that in mind. We're talking about a few tens of microseconds in the plots that I'm showing here. But this is just makes it easier to see. So we get one destructive interference null, and we get two constructive interference points from a two sample delay. And here's three sample delay. Unfortunately, this is level 2 and this is level 2. I forget where I borrowed these figures from, but unfortunately, they didn't normalize the heights of these. I wish they were. So I wish this did not go up to 2.5 and this just went all the way up to 2. So anyway, we now see two destructive interference points, and to constructive, and then 4 samples. So as the delay gets larger, we get closer spacing between these, and we get more and more and more of these. If we went up to a much larger number of samples, we'd see lots of these nulls and peaks. And in fact, if you analyze this, you don't have to make it time variable, just make plots like this using freq z and try out different values here, a different number of samples to see, and you'll see that you get very significant number of spikes and nulls. Now, what about the LFO? And I'm saying shapes for flanger, and then I'm alluding to something we'll talk about in just a little bit. So just cycling back so I don't have to talk about LFOs again for chorus, but that'll be a later function that we'll talk about in just a few slides. So for vibrato, we said we almost always use sine. But for flanger, there's 3 that are common: sine, triangle, and sawtooth. The reason this one is red is that I had to do some editing of the diagram. So it's not saying that there's anything more important about sawtooth. So there's the 3 common shapes. So that's a little different than for vibrato. Vibrato almost always uses the sinusoid. So these will change the sound of the flanger, and later we'll see of the chorus. Okay, so that's about all we have to say about the LFO for this. Another thing we can do, and is common in many flanger implementations, wasn't necessarily easy to do in the old school with version with the reel-to-reel tape players, but once we started making these electronically, you can feed back the delayed thing to go through again. Now, this delay here is going to be short compared to what we saw for the echoes. Because remember, if we get rid of this down here, we've basically got the echo. And then, this gives us the original, and this would just give us echoes over and over and over again. We just didn't have the LFO in that. But here, for flangers, as we'll see in just a minute, the delays are pretty short. So we don't experience these as echoes. Remember, I showed a table that showed the range of delays, and the top entry was comb filter. Well, that's what we've got here. We've got a comb filter. So we don't really hear this as a repeating echo. It's just going to change the shape of the frequency response. So the shape of the peaks and the nulls will be modified to some degree, and it can create interesting sounds. And if you want to write the difference equation and look at this, you can. And again, you could, explore this for various fixed values of the delay just to see what this thing is going to look like. And you can play around with different values of those feed forward and feedback. And there's the transfer function if you want to look at that. So, like I said, we are typically using short delays. So let's look at some of the parameter values here for flanger. So as we already said, our waveform shapes can be one of those 3. Sine is kind of the default, but the other 2 give some interesting sounds. The LFO frequency is usually pretty low, 0.1 up to 10 hertz. Remember, that's not trying to make a wiggle like we did in vibrato. It's just trying to sweep those nulls. So we can set it really low, and you'll hear those nulls sweep through the sound. So like I said, listen to the song Barracuda, and you'll hear that's a pretty low LFO frequency. The blend value, so that's this GFF. That's this part here that blends what's coming through the delay and the original. That's what's going to set the level of the notches, right? So if we set it equal to 1, then we get complete cancellation at the frequencies where there's destructive interference. So that's going to give much deeper notches. So you can almost think of that as a depth effect. How much depth is there to the effect? And then here's the delay value that I alluded to up here. We're talking about up to about 10 milliseconds. And so if we go back and look at our relationship between the parameters for the filter, the comb filter, and the spacing of the zeros and those gaps, we can see where these notches occur. And so with this range, 1 to 10 milliseconds, the notch spacing would be 100 to 1,000 hertz. And that's going to be uniform across the entire frequency response. So if we had 1,000 hertz spacing, and we're going from 0 up to 20 kilohertz, that's going to be 20 notches, right? And if we go down to 100, it's going to be 2,000 notches. So it's a lot of notches. And so that's the sound that we're getting, or the frequency response kind of shape that we're getting from a flanger. We don't hear it as delay. Here we hear it as the notches. So again, go back and look at that that table that we started off this note set with. Well, let's actually do that. Let's go all the way back. There it is, right there. So we're talking about flangers running down here, and then echoes running up in that range. And we didn't even go up to 20 in the slide that we just talked about. So that's the idea. So keep that in mind. Okay, chorus and doubling. So flanger used two signals added together, but not with the intent of making it sound like there's two. We're just canceling. We're using one to cancel frequencies of the other one, and we change as a function of time where those notches are. That creates that changing whooshing sound. But here we're going to try to mimic having multiple voices that are singing in unison, but with some slight differences. So I already said John Lennon was famous for this. He didn't like the sound of his voice, and he always asked the engineers, at least after they started getting a little bit famous and they could ask engineers to do things, hey, can you record me again? And I'll try to sing it exactly the same, and then we'll mix those two things together. And he liked the sound of that. And then he ultimately asked the engineers to just do that electronically, so he didn't have to try to do that. So time varying delay is going to be involved because we don't just want to move a fixed delay. We kind of want to have it just wander ever so slightly from the other version of the signal. So we already know how to do that. Time varying delay with interpolation. So that looks like the thing we've been looking at. Looks like a flanger. Okay, but the difference now is these delays that we're talking about here are going to be longer than the delays for a flanger, and the LFO is not going to sweep them over such a wide range as we saw before. So looks like a flanger, but the difference is in the parameter values. And so here are some ideas that show that. So vibrato and flanger, very small range of delays. Now we get up to chorus and doubling, and now we're into some other slightly larger. Now there is some overlap, right? But primarily chorus and doubling, longer delays, vibrato and flanger, shorter delays, and then echo, much longer delays. So that's what one structure set things differently. We get 1, 2, 3, 4, 5 different effects. That's the idea. And we can make multiple voices. We could do this for chorus. We could do it for doubling, in which case it's not doubling, but it's tripling, quadrupling, whatever. So And they can be running with LFOs that are not related at all. And so you can add as many voices as you want. You just need more memory locations and more LFOs to do that. And that leads us to the last slide of this note set. Everything we've talked about can be built with this basic structure. This comes from John DeToro's paper, as does this table. And it just shows how you can set these things to different parameters. We've got our interpolated delay line. We're drawing from some fixed tap for the feedback. We're drawing from some moving tap for the feed forward, and we're blending something in. And by setting these different parameters here, we can get various different effects. Now, it's been a while since I've read John DeToro's paper. I can't really remember from a perception point of view the difference between industry standard chorus and white chorus. So if you're curious about those, get a copy of that paper. I think it's out on the internet. You can probably find it as a PDF and read it and find out about that. So that is delay-based effects. You'll notice if you are a guitar player, you might be saying, hey, where's the phaser? That's not a delay-based effect. Even though it sounds an awful lot like a flanger, the phaser is implemented differently. So they sound similar. There are some subtle differences, and that's because they are different effects. But it's hard sometimes to, especially when they're employed subtly, to say, is that a flanger or is that a phaser? So in the next set of notes, we'll look at phasers, and we'll look at a couple other things that are implemented in using techniques that are used for phasers. So I hope to see you there.